So we start with the next session. So the long-awaited session of Professor Venketeshwar Pai. His brief introduction: he is Associate Professor at the Department of Humanities and Social Sciences at Indian Institute of Science, Education and Research, Pune. He has PhD from IIT Bombay. His research interests include Indian astronomy and mathematics. He is a recipient of Young Historian of Science Award of the Indian National Science Academy in 2014. He is also a member of the Indian National Young Academy of Science. And the topic for his presentation would be Understanding Vākyas through Karaṇapaddhati of Putumana Somayājī. So over to you, please.
Hello, namaste to all. First of all, I thank the organizers for providing me an opportunity to talk in this conference. So I'm more comfortable like this. So the topic is understanding Vākyas through Karaṇapaddhati. So yesterday, people have talked about Siddhāntic astronomy and Purāṇic cosmology and so on. So when we say Siddhāntic astronomy or Siddhāntic astronomical literature, it means comprehensive astronomical literature which starts from the time of Aryabhata. So people have talked about Aryabhatiya, Bhaskara, Siddhanta Shiromani, etc. So as far as Indian astronomical literature is concerned, based on the mathematical complexity involved, we can divide them into two broad categories. One is called Siddhantas, which are more mathematically complex, they are more theoretical in nature, and the other category is Karanas. Karana means, they are astronomical manuals by which one could find different astronomical parameters with ease. So, Vākyakaraṇa, there is a text called Vākyakaraṇa of 12th century, whose authorship is not known, where author says that we can divide this astronomical literature into four parts: Siddhantas, Tantras, Mahatantra, and Karanas. And Karanas, as I told, they are more simplified versions. They just give simplified algorithms to compute different planetary or astronomical parameters. Whereas Siddhantas are more comprehensive in nature, more theoretical in nature, and Karanas, they don't give any rationale for their algorithms, or they're just you'll find just based on four mathematical operations, one could arrive at different parameters. Whereas in Siddhantas, we need to have need to apply the sign functions, and it becomes more complex. So it's for Panchanga-kartas, the Karanas becomes more handy. In this context, the text Karaṇapaddhati is very much important, because Karaṇapaddhati, etymologically, Karaṇapaddhati is Karaṇapaddhati. The first Karana stands for the Karana class of literature. There's a Karani to do or to compose. The text Karaṇapaddhati gives the Paddhati for composing Karana text, which means it also gives the mathematical rationale behind Karana text. It also talks about a new system called Vākya system, and Karaṇapaddhati gives rationale for different parameters pertaining to Vākyas or Vākya system. Now, what is Vākya? Vākya literally means a sentence or phrases in the context of astronomy, it represents a mathematical quantity or an astronomical quantity. The earliest Vākyas that we can trace back are known as Vararuci Vākyas, or they are also known as Girnashrayādi Vākyas, and they are also known as Girnashrayādi candra-vākyas. That has something to do, since there has something to do with the moon, they are known as candra-vākyas. It starts with the Vākya Girnashrayaha, which is known as Girnashrayādi Vākyas, and this is composed by Vararuci, hence it is known as Vararuci Vākyas. So these are the typical example for Vākyas. So here you will find there are 248 Vākyas starting from Girnashrayaha, Dhenamashrihi, Rudrastunamyaha, Ramadhiyate, and up to Dvayachikam. So there are some number encoded in this Vākyas based on one of the numerical system of numerical that is known as Karaṇapaddhati system. Karaṇapaddhati system is, remember, Kata, Ka, Yadi, Adi is etc. Kadi means Ka is one of the consonants. Ka, Kha, Ga, Ga, Cha, Cha, Ja, Ja, Nya. So there are 10 consonants. So the numbers 1 to 0 are assigned to these consonants. Ka, Kha, Ga, Ga, Cha, Cha, Ja, Ja, Nya, from 1, 2, 3, 4, 5, 6, etc. up to 0. Similarly, Tadi and Padi and Yadi. So here, so you can see Gi, Ga means 0, Ga means 3. Na is 0. Shre, you have only, one has to consider only a consonant which is proximate to the vowel. So Ra is 2 as per the system, and Ya is 1. And if you reverse the order, you have 0, 0, 1, 2, 0, 3, because only there are 4 syllables in this particular Vākya. Only there are 4 syllables. So you have the first quantity is 0, 0, 12, and 0, 3. And all these quantities or all these Vākyas represent the true longitude of the moon. From one particular day up to 248th day, which means the first day after some event that will, which is known when the moon's anomaly becomes 0, the one has to start counting from the Vākya when the moon's anomaly is 0 at the sunrise. I'll talk about what is moon's anomaly. So this is suppose this is the Earth, and moon revolves around the Earth, and this is moon's apogee, where moon's motion is least. This moon, the moon's apogee is also revolving in an opposite direction. So when moon coincides with its apogee, it is called one anomalistic revolution. So we'll have approximately 9 anomalistic revolutions in 248 days. We'll see how we'll obtain this number later. So that's the significance of this 248 Vākyas. From the day when the anomaly of the moon is 0, longitude of anomaly, which means that when the moon is in conjunction with its apogee at sunrise, one has to assign these Vākyas. And as I told, these are true longitude, and this represents the sign or the Rashi. This is in degrees and this is in minutes. This 00 Girnashraya is the first day. Moon's true longitude is 00 Rashi is 12 degrees and 3 minutes. And on 24th day it is 6 Rashis, 13 degrees and 52 minutes. So as I told, this is how this is the 248 you can see here, that we'll see later. And where these Vākyas are used, these Vākyas, they don't actually, okay, the Vararuci has given these Vākyas as it is, but the text Vākyakaraṇa gives a detailed procedure to use these Vākyas to obtain the true longitude of the moon at any desired day, using a Vākya system. So before that, I'll just briefly go through the Siddhāntic procedure for finding the true longitude of a planet, or in this case of moon. So there are 3 steps which are involved for finding the true longitude of the moon. First is one has to calculate the Hargana. Hargana is the time. Suppose if we want to find the true longitude of a moon for today's date, we need to find the number of days elapsed from the beginning of Kali till today's date. So that is known as the Hargana, and one has multiplied that with the number of revolutions by the moon made in the Mahayuga and divided by the number of civil days in the Mahayuga. So some people have talked about what is a civil day, and find the fractional part and multiply that with 360, we'll get the mean longitude of the moon. And then one has to apply a samskara, which is known as Manda samskara. It is in fact, it takes care of the eccentricity, and it's also known as eccentricity correction. And this is the Manda samskara, which is to be applied to the mean longitude, so that you obtain the true longitude of the moon. So here we can see that sine function is involved, and as far as moon's longitude is concerned, only Manda samskara is applicable for the sun and moon. But in the case of planets, both Shikhar samskara and Manda samskara are applied to obtain the true longitude. So the text Vākyakaraṇa. So in any Vākya text, they first give the quantity called khanda. So khanda is an important parameter which is used in the Vākya system. Khanda, this is how they give. So in Vākyakaraṇa, the text Vākyakaraṇa gives this khanda as Vedadajnana. So this is again from Karaṇapaddhati, one can obtain 1600984. This is the number of civil days from the beginning of Kali. At this point, the anomaly of the moon would be 0 at the sunrise, approximately 0 at the sunrise. It also gives something known as dhruvas. These are the different dhruvas and khandas. So using these 4 and 5 quantities, one could obtain the true longitude of the moon. So what one has to do is find the khanda sesha first. So we have ahargana, which is the number of, suppose ahargana is the desired the time, civil days, number of civil days elapsed from the beginning of Kali till the desired day. That is ahargana. From ahargana, one has to subtract something what is given as khanda here. So one has to find a minus a dash. A dash is the khanda, is the textual value. A is the ahargana that is to be calculated, for which the moon's longitude is desired, and that has to be divided by 12372. So again, I'll go back to the previous slide. So in the same table, you can see that this 3031, 12372, 188611, all these numbers are used to obtain the in the procedure for obtaining the true longitude of the moon. So all these numbers are nothing but the number of days which are required to have integral number of anomalistic revolution of the moon. Yes. So first, so these are different days corresponding to different anomalistic revolutions. So first one has to divide this by 12372. Then we have a quotient, that is Q1 and R1 by 12. Okay, R1 is the remainder. Again, R1 has to be divided by 3031. Then we have Q2 is the quotient. You have to store that. Again, remainder is R2 here. R2 by 248. The quotient obtained is Q3. And one has to multiply all these quotients with the dhruvas. Dhruvas are nothing but the number of the longitudinal change in those 3 number of days. The longitude here means the position of the moon from the measure rashi or any fixed point. So di, what we obtain is d1 into q1 plus d2 into q2 plus d3 into q3, and d3 is d0 is the dhruva at the time of khanda. So khanda is ideally a point, or khanda is a day, which is mentioned in the Vākyakaraṇa 1600984, on the day in which the moon is in conjunction with its apogee nearest to its sunrise. But it actually ideally khanda to be defined like that, but in actual practice it may not happen. There will be a time difference between the conjunction of the moon and its apogee and the sunrise, which means at the sunrise on the khanda day, there will be some finite value of the longitude for the moon, and that is the dhruva corresponding to the khanda. Okay, and so that has to be added to this value. and plus one has to so here this Q3 has been obtained by dividing R2 by 248, which means there are VR3 is the remaining number of days which is less than 248, where Vākya has to be applied. For example, Vākya, so R3 is 124, then VR3 is 06 Rashis, 13 degrees and 52 minutes. This is how the true longitude of the moon is computed using Vākya system. So now, I'll just show an example quickly for say today. So Nija Ashara Krishna Navami, August 6, 1969. So A is 1851 974. Khanda is 1600984. One has to find the Khanda Shesha, that is this much. That has to be divided by 12,372. So quotient is 20, and then R1 has to be divided by 3031. Quotient is again 1, and remainder here is 590. That has to be divided by 248, and remainder is quotient is 2, and remainder is 23. So having applied this, substituted those values in this formula, we have 81.04 degrees. That has to be the Vākya. So and here R3 is 23, which means you need to consider the Vākya 23, which is Goraso Nanusyat, which is 10 Rashi 7 degrees 23 minutes. That is 307.38 degrees, which is the longitude of the moon at the time corresponding to the Vararuci 1851-974. So now the question is here, the Khanda, all these texts, they just specify the Khanda, they specify they just tabulate the Dhruva values and give the procedures to compute the longitude of the moon and other planets. But how do we obtain, so what is actually Khanda means? This is the pictorial representation what I had already explained. So this is the Vararuci. Khanda is the period in number of civil days. So this is the Khanda, where this is the day at the end of Khanda, where the moon and its apogee are in conjunction, and also in conjunction with the sunrise. Ideally, it should be like that, but there should be, in actual practice, there should be some time difference between the conjunction and the time of the sunrise. So now, so the term Khanda literally means section or segment or a part. When it is used in the context of longitude of the planets using Vākya method, is the part of Ahargana that needs to be subtracted from full Ahargana in order to obtain a certain quantity known as Khanda Shesha. So is this choice arbitrary? No. So a Khanda represents the closest epoch to the Ahargana in the recent past on which Mandaka Kendra or equivalently the equation of center is 0 at the time of the mean sunrise. So now the Karaṇapaddhati gives all these Vākya texts they just specify the value of the Khanda and value of Dhruvas and the procedure. But the Karaṇapaddhati gives the rationale for obtaining this Khanda. Also, they gives the these successive approximations. So here you can see this is the quantity is based on the Karaṇapaddhati parameter, the number of anomalistic revolutions of the moon, and moon revolves takes these many number of revolutions, anomalistic revolutions in these many number of days in a Mahayuga. So all these numbers are successive approximations to that, which means this number divided by this number is approximately same as 9 by 248 or 110 by 3031, but they are all approximations. So now, as I told, the Karaṇapaddhati is the text which gives the paddhati or the process or the mathematical rationale to compose Karana texts. So one of the main mathematical concept or the tool which is used in Karaṇapaddhati is known as Valyupasamhara. Using this method, Valyupasamhara, the author Putumana Somayājī solves different astronomical problems. So one of the main aim of this Valyupasamhara is to give the successive approximations, and also using the properties of Valyupasamhara, which is equivalent to something known as continued fraction in modern context. he makes use of the properties of continuous fraction to provide different to give the mathematical rationale for different astronomical concepts such as khanda, etc. So here I have taken an example, taken the example of khanda. So this is how the Valiva Samhara goes. Anyonyāhrata bhāgyahāraka phalam sarvam tadhodhvanyase ekapradya phalena hīnam aparaprayakam dvayostopari kuryāt Valiva Samhatim vihuparitah purvapranāsam vinam tyājyam tat prathamodhvagam haraguna shishtastas vasvechaya. So anyonyāhrata means the mutual division. So suppose I have a quantity, say h by g, so you have to divide them mutually. So first divide h by g, then you have a quotient and you have a remainder. So suppose the first quotient obtained is q1, then you have remainder r1, and then again divide it by the previous say g, then you have q2, then you have to continue this process. So continue the process of mutual division, then you will have a successive quotients q1, q2, q3, etc. up to qn. So this is the first step. Then second step, what one has to do is we have to place a 1 before this first quotient. The first quotient that has obtained is q1. Before that, above that, one has to keep 1, and in the second step, 1 and q1 has to be kept as it is. The third row would be q1 into q2 plus 1. Okay, and in the third step, you have q1 into q2 plus 1, and the fourth row would be q1 into q2 plus 1 into q3 plus q1. So one has to multiply the this quantity with the previous quantity and add the penultimate quantity. So one has to continue the process. So at the end, you have q1 into q2 plus 1, q1 into q2 plus 1 into q3, and or hn equals hn minus 1 into hn minus 1 into q1 plus hn minus 2. Okay, and you have to delete the 1 which has kept above in the initial at the initial state. So this is how you get the successive divisors. These h are the successive divisors. Why h? Because haraka is the term used for divisor, so that's why we have taken divisor as denoted as h. Similarly, one can generate the multipliers keeping not considering q1. The first in the first line or the first column you will have 1, then you will have q2 instead of q1. Okay, but the process is same. In the second column you have 1 q1, 1 q2, q2 into q3 plus 1, etc. And third column you have 1 q2, q2 into q3 plus 1. Fourth column q2 into q3 plus 1 into q4 plus q2, etc. And you have in the final column you have g1 is 1, g2 equals q2, and so on. So gn equals gn minus 1 into q1 plus gn minus 2. So this is how the successive multipliers can be generated. So by applying this to this particular case, in the case of anomalistic revolutions of the moon, this is the G's, and this is the H, G and H. So if you do the Valiva Samhara for these two quantities, you will have successive approximations, Gi's and H's here. They give the approximate number of anomalistic revolution versus the days in which that many number of anomalistic revolutions happen. Okay. So this is how the successive approximations of any two ratios could be found. So now, as I told in the Vākya system again, the term khanda is very much important, and so Karaṇapaddhati also gives the rationale for how to obtain the khanda. So this is how it gives Devendra Sharnaikya, Dinendu Tunga. So first find the theta 0 is the mean longitude of the moon, theta m is the longitude of the apogee, at A is at the Haragana. At the time of Haragana, one has to find theta 0 minus theta m, and it has to be added to theta 0 minus theta m for 303 days. Okay, and it has to be multiplied with any hi. Hi is one can choose. These are the values of hi. One can choose any divisor from this this column hi. If you choose, say, some hi, and that one has to consider the integer. One has to take the integer part of it and it has to be multiplied by hi minus 1. The previous, if you choose I as 3, then hi minus 1 is the divisor corresponds to the I minus 1, that is 2. And it has to be divided by hi again, and remainder would give the khanda. So, and that remainder has to be subtracted from A if the hi's are odd. If hi's are even, then hi minus ri has to be found, and it has to be subtracted from A, which would give the khanda. Okay, so okay, now this Karaṇapaddhati gives this algorithm for finding the khanda. So if we try to understand the rationale, mathematical rationale for this khanda, we can see that without the knowledge of the properties of successive convergence, relation between successive convergence, these properties of continued fraction, gi hi minus 1 minus hi gi minus 1 is minus 1 all raised to I plus 1. Without the knowledge of this, one could not arrive at this algorithm. Yeah, thank you.
Any efforts to update the Vākyas?
No, we should.
No, Madhava's.
Okay, Madhava's question is there. The Madhava's question of Vākyas again, not contemporary, but we don't have contemporary.
Minutes he went to seconds.
Seconds in 14th century.
Anybody currently now?
Which one? Yeah, so I'm working on the text Vākyakaraṇa and translating and providing detailed explanatory notes.
Where?
I'm working at IISER Pune. Yeah.
IISER.
Okay,
Stay there only. See that.
okay. Siddhāntic, I know. Yes. It's humanities and social science.
Thank you so much, Professor Venketeshwar Pai. You have very well established with example the simplicity of Karaṇapaddhati as opposed to Siddhāntic computation complexities. And you also showed proper examples to calculate the longitude of moon. Thank you so much for sharing all the details.